Thank you. Thanks a lot for being here. My name is Raúl Kripalani. I'm the tech lead for the libp2p project from Protocol Labs. It's super exciting to see so many people in the room that are actually interested in peer-to-peer networking. This is, as I said yesterday in the panel, I don't know if you heard it, it's traditionally been kind of like a niche area of technology, which as we continue building new layers of decentralized systems and creating stacks upon stacks upon stacks, we are realizing that the foundation of everything is really the core, the networking. If we don't have a strong, rock-solid networking layer that is resistant to all kinds of attacks, that is extensible, that is modular, that is future-proof, and so on, we really have nothing, right? So this is what I'm going to talk about today. I'm going to talk about the libp2p project. Who here has actually used the libp2p project? Who is a user of libp2p? All right, we have one hand in the room. This is amazing. So this is a testament of what I was saying, right? It's kind of like peer-to-peer networking, and I know that I have more people over here who haven't, who are a bit ashamed today. But this is kind of like a testament of what I was saying, right? It is peer-to-peer networking tends to be so invisible to the naked eye that very few people actually dig their hands deep into it. Who has heard about libp2p before? Whew, okay, that's better. All right, so let's get started with this. I have a lot of information to share with you today, so I'm going to do like a very high bandwidth, high throughput delivery of this. If something is not clear, feel free to find me later. So libp2p. So what we're going to go through today, this is the agenda for today. I'm going to do a quick introduction to libp2p. Then I'm going to walk you through the different elements of the stack, the different layers of the libp2p stack. So that's addressing an identity, transports, connection bootstrapping, secure channels, multiplexing, protocol negotiation, peer discovery, content routing, pub/sub, connectivity, and we're going to talk about the future. Actually, we're going to talk about the future all throughout. So whenever you see this little crystal ball, that means that it's a feature that is projected for the future, and hopefully the future will come soon for many of these things. All right, so what is libp2p? So libp2p is a modular peer-to-peer networking stack. I like to explain it to people as a set of composable building blocks that application developers, platform developers, decentralized systems developers can assemble to create the right stack for the right networking stack for what they need. It is really puts a focus on this composability aspect, on the extensibility aspect, and of course on future proofing. Because one problem with current networks is, and the current networking system, and in general the current networking architecture of the internet, is that it's unfortunately very ossified. So this means that decisions taken 20 years ago without the understanding of what the internet would turn out to be in the future and how important it would be to humanity are actually affecting us very greatly today. So libp2p puts a focus on future-proofing. It runs on many runtimes, server, browser, mobile environments, where there have been experiments, and soon there is a libp2p implementation that is going to be very suited for embedded devices. libp2p originally originated in the IPFS project. Who has heard about IPFS here? Fantastic. Okay, so libp2p was the networking stack of the IPFS project that Protocol Labs decided to extract from IPFS and turn it into a general purpose networking stack for other projects to build upon. It's implemented in 7 languages and it has currently a bustling and a flurry of activity that just keeps increasing in the community. It was created and stewarded by Protocol Labs, but it's really, we think of it as a public good. It's owned by the community. It's currently licensed under the MIT license, but it's soon moving to the permissive license stack, which is a combination of the Apache software license and the MIT license to avoid any uncertainty with regards with patents and so on. So as I said, I like to explain libp2p as a set of composable building blocks. And these are the ones. I'm not going to go over those again because I already did in the agenda, but you can see that it's like kind of like a Lego puzzle of different pieces that fit together to build the right networking stack. So who's actually using libp2p? Of course, IPFS, Polkadot, Ethereum 2.0. You've probably heard about this in several presentations already. Is using libp2p, Filecoin, MetaMask, OpenBazaar, 0x, and so on. And there are a number of projects that are considering libp2p as well, like Cosmos, the Coda Protocol, and Matrix, who is experimenting with libp2p. So I'm pretty sure that everybody in this room would have heard about several of these projects. What's cool about libp2p is that, and especially about having these many adopters, is that these are active people who are getting involved actively in building the future of libp2p. So really, when you look at the networking stacks of all of these projects separately, and you put like a magnifying glass on each of these, they look a lot alike, right? And we'll talk about this in a second by going through what is actually needed to make peer-to-peer networking happen, right? So it's great that, you know, all of these projects are unifying efforts and really building a foundation that works for everybody, right? And pooling resources, there's no point reinventing the wheel everywhere, right? So this is what libp2p aspires to be as well. So as I said, libp2p has currently 7 native implementations. We've got JS, Go, Rust, PyLib2p. I think we might have some of the PyLib2p implementers in the room, if Alex Stokes is here, and Kevin and Xiaowei. They all have contributed to PyLib2p. We've got JVM libp2p. By the way, Rust libp2p, we've got one of the contributors to Rust libp2p here as well. So, you know, it's a bustling community that just keeps growing. And what I'm really excited about is particularly several of these implementations here. The JVM libp2p implementation is going to be the base for Android specialization, for mobile specialization of libp2p, and NIM is going to be specially workable for embedded devices. So much of the traction of libp2p is coming from Ethereum 2.0 adopting libp2p for the networking layer. So I don't know if you've seen this spec before, but here is, in case you wanna search for it, it's under the ETH 2.0 specs repo. You'll get to see how libp2p is actually being used in Ethereum 2.0. And as I said, so Ethereum 2.0 is a multi-client effort where these clients are implemented in different languages, and all of the teams that are implementing ETH 2.0 are also contributing actively to the libp2p ecosystem, which is amazing, right? So one of the philosophies of libp2p is this thing that's called decentralized process addressing, right? So if you think about the current internet, it revolves around the concept of location addressing, right? So there's always an IP address, there's always a port, there's always a protocol, and you always hit a process that's sitting on a machine of which you have the locator. Decentralized process addressing kind of turns that around. And the reason to be of libp2p is really, or kind of like the guiding star or the North Star of libp2p, is the ability to locate, connect, authenticate, negotiate, and interact efficiently with any process in the world, no matter what the runtime is, right? So it could be server, browser, IoT, and so on, so long as its identity is cryptographically derived from its public key. And libp2p really strives to make all of this happen in a seamless manner. This is not the current case right now, but this is where we want to get to, by making all of NAT, relay, packet switching, and a number of things transparent to you, such that as those processes relocate and roam around the world, you'll still be able to address them by process ID. Now, how does this, so let's start getting into the technical details of libp2p. The first thing, kind of like the building block, like one of the main building blocks of everything, is addressing. How do we actually address these processes in the world? There is the concept of multi-adders, which are essentially composable, future-proof. I don't know if you get to see the coloring on these slides. Unfortunately, it might be a bit difficult to see, but a multi-adder is a composable, future-proof, upgradable, transport-agnostic address. So if you think about how we address processes in the world, we usually have an IP address, a port. You need to know if the thing that's running behind is using TCP, it's using UDP, right? If in the future you wanted to communicate with the same process over a different transport, like WebSockets or Bluetooth or you name it, you would have to modify your protocol because Bluetooth doesn't have IP addresses, right? It has MAC addresses. WebSockets, for example, has ports, right? So, it has context paths, right? And a number of things. So you would need to modify your protocol. How do you avoid this? Multi-adders is kind of one way of doing this. Basically what it does is it creates a binary, so you replace all of these IP addresses, ports, and all of these like granular things with just one byte string, right? And that byte string is extensible, and it represents exactly it encodes the different aspects of how you address that particular process in the world. So the IP address, the TCP, what network protocol you're going to speak with that process, the port number, its identity, and so on. And multi-adders are normally represented in this like string notation, but when they are part of messages and protocols, they are really byte-packed. So really hinging on this idea of multi-adders and the hierarchical system for naming process in the world, who here has heard about Plan 9 as an operating system? Cool, a few people, mostly the protocol developers, that's great. So Plan 9 is an operating system that was developed by Bell Labs, and it had this really cool concept of and this cool notion that everything is a file. So you can imagine the hierarchical nature of multi-adders being able, like if you were able to mount the entire world, right, that is addressable via multi-adders onto your file system and have kind of like a daemon such that whenever you open a file descriptor or you write or you read from a file descriptor, behind the scenes is actually using libp2p to make that connection happen. That is kind of like a very cool idea, right? So this is really the inspiration behind, the nature of multi-adders. Ideally, I would love to be able to mount the entire peer-to-peer world's network on my laptop and be able to like interact with it via simple file descriptors. So a key concept within the libp2p networking stack is peer identity. And peer identity and peer IDs are derived from public keys. And libp2p supports 4 different types of public keys. There is nothing preventing you from adding a 5th, a 6th, 7th type cryptographic keys of key types. But of course, you would need to do that across all implementations because otherwise you'd break interoperability. Now, the way that a peer ID is formed is essentially there is a little protobuf struct which you inform with a key type and the pub key, and you hash that via something that's called multi-hashes, which are future-proof hashes that basically prepend the type of the hash, what the hash function was, what the digest function to generate the value was, just to make it self-describing. And normally we indicate peer IDs and multi-adders. So whenever you address a process in the world, you also indicate what the peer ID is of that process. Now, when I talked about making connections actually happen, right? So how does the libp2p stack really create those connections? It has the concept of transports, and transports are basically a core abstraction in libp2p. You should really think about them as connection factories, right? So they are capable of dialing an address, which is the term that we use to connect outbound to a peer, and listening for inbound connections, right? So a transport actually produces raw connections. It's kind of like the layer 4 of libp2p. And currently we have 4 transports with different levels of maturity, TCP, QUIC, WebSockets, WebRTC. And in the future, coming to a node near you, we'll be having really stable and ubiquitous QUIC, which is important, especially when you combine. So has anybody heard of HTTP 3? Cool. So if you've heard of it, you will know that HTTP 3 basically uses QUIC as the underlying transport and uses TLS 1.3 as the security channel. So by making QUIC and TLS 1.3 pretty predominant in the libp2p network, and potentially making those processes run on port 443, we essentially get a pretty good means of censorship protection, right? Because all traffic essentially looks like HTTP 3. I mean, censorship protection in terms of censorship resistance, in terms of deep packet inspection. Now, transports, other transports that are coming in the future, Bluetooth, via our friends at Bertie. Bertie is a company that's developing an offline-first chat platform, and they've created a Bluetooth transport for Go libp2p, which is amazing. UTP, we're working on message orientation as well. And what's cool about the multi-adder concept is that as you create and as you add support for new transports into a libp2p stack, they just get represented as one token in the multi-adder. If the peer supports it, if the current implementation supports it, it will be able to dial and listen. If it doesn't, well, it probably has a lot more transports that it could use anyway. So imagine you've got a multi-adder, right? And this represents a peer somewhere in the world that you want to interact with. How does the dialing process actually work? So the first thing that happens is, so if you look at this multi-adder, it's basically saying, hey, I want to contact the process in IP address 1.1234 at this port number. I'm using TCP, and this is their peer identity. Right? This is their peer ID. Now, the way that this happens is we first use a transport, the TCP transport, to create that connection. The TCP transport gives us a raw connection, which we then upgrade into what we call a capable connection. Right? So a capable connection is one that's authenticated, that's encrypted, and multiplexed. We're going to talk about all of these things in a second. Right? They might be like very foreign terms for you if you haven't heard them before, but we're going to go through this. So the first thing that we do is negotiate on what secure channel we're going to use with that peer, and then we negotiate a multiplexer dynamically. This is important because it makes the whole system future-proof. If we find a bug, if we find an issue, if a particular security protocol is broken, if you hard code the usage of a particular security protocol or a security handshake, then you've ossified the protocol already, right? So making that change in a peer-to-peer network is super difficult. A peer-to-peer network, you don't control the network. Right? So by definition. So and like Juan Benet, the founder of Protocol Labs, once said, peer-to-peer network is not only a network that you don't control, but it's going to actively try to attack you in all possible manners. Right? So you got to make sure that every aspect, every step of the way is dynamic enough so that it can be changed in the future if it needs to change. Right? So what's important to say here as well is that some transports don't actually need upgrading. And Quick is an example of this. If you've heard of Quick, then you will know that it's multiplex and encrypted by default. So we can avoid making this upgrade because the transport already gives it to us. This is kind of like a diagram, a sequence diagram of how this happens in reality with multi-stream select 1.0. I'm going to talk about the future now. If you want to read stuff like this and you're interested in like understanding the nitty-gritty details of how this happens, then go to the libp2p specs repo and you'll find all of that information there. I'm proud to say that it is in a much better state than 4 or 5 months ago, where it was pretty, in some cases, undocumented. So yeah. So okay, one of the things in this process is the security channels, right? So a security channel in libp2p provides two things. It provides peer authentication and it provides transport encryption, right? And well, other things like transmission integrity, non-repudiation, and so on. Different security guarantees. It depends on the protocol. All implementations support something that's called SecIO. And some implementations support TLS 1.3. And there is also a secure channel called plaintext for testing. You should never run a plaintext channel in production. But this is useful if you combine it with something like Wireshark and you want to see what's actually happening on the wire as your libp2p node is running. Okay, so those are the current secure channels, and what's coming down the pike are two things that I'm super excited about. We've got wide support for TLS 1.3. There are some roadblocks in some implementations, like Rust and JS have a few roadblocks. TLS 1.3 is available 100% in Go libp2p. Still hasn't been rolled out to a live network, so still needs to undergo considerable testing. And another one that I'm very excited about is noise handshakes, which, who here has heard about the noise protocol framework? Cool. Protocol developers again, excellent. So the way that we've adopted noise is pretty interesting because we're using something called noise pipes. I'm not going to go into it, but I will say that noise handshakes are a requirement for Ethereum 2.0 mainnet. So we're definitely collaborating. And there's other actors in the space like Cosmos who are also interested in this. All right. So I mentioned this term that might have sounded a bit alien to some people, which is multiplexing. Okay, so the first thing that you need to know about a peer-to-peer network is that establishing a connection with a peer is difficult, expensive, and negotiating with that peer is not easy. So we want to amortize the cost of establishing a connection, right? Which means that if I've got a connection and I want to talk different protocols with that peer, different applications, for example, or I want to have different conversations with that peer, parallel conversations. I don't want to establish a connection for each because I don't want to undergo the cost of each. So what I do is use something called multiplexing, which basically, here's a really nice diagram of how multiplexing actually works. So you can imagine a connection, a single connection, opens up and becomes a strand of multiple parallel conversations, right? Which are isolated from one another. And this is what multiplexing gives you. We've got 4 implementations of the multiplexing layer: YAMX, MPlex, and Speedy Stream and Quick's native multiplexing. And in the future, we are considering adding support for something called monoplexing. For those applications that don't actually need the multiplexing support, we don't need to negotiate a multiplexer, and I don't know what happened there. Okay. All right, so another thing that's interesting as well that I wanted to discuss was protocol negotiation. So protocol negotiation, and so once you establish a stream with a peer, once you establish one of these conversations with a peer, you want to agree with them what is the thing that you're going to talk about, right? And that is what we call a protocol. You negotiate a protocol with a peer. Right now, we use multi-stream select 1.0, which is a interactive, chatty, speculative, and we're going to be moving soon to multi-select 2.0, which gives us a lot of cool features, fancy features, such as one round-trip connection establishment. Right now, establishing a connection with a peer is kind of a bit interactive and chatty. So we'll be moving to the scheme in probably a few months from now. It's gonna give us as well cheap repetitive protocol selection, upfront negotiation, session resumption, and a number of things that we're specifying in this issue, in this pull request. If you're interested in digging deep into that. So each of these conversations that peers have with each other are identified by protocol ID. So there's protocols like FlupSub, FloodSub, BitSwap, and so on. Normally they have a protocol ID is just a string. Right? It doesn't actually need to follow a particular format, and you can think about it as REST endpoints, right? So when I establish a connection with a peer, I want to address some functionality in that peer, and that functionality is identified by a protocol ID. Wow, though that color choice was really bad for this particular room, right? So we've talked about. Up until now, we've talked about 2 peers establishing a connection to one another. But you have to realize that in a peer-to-peer network, there is no central authority, there is no central directory of peers, you don't know who's out there, right? So you need to discover who's out there. And libp2p provides an abstraction called peer discovery. And it's basically a very simple interface that can be backed by many implementations. So one implementation of this interface is a DHT, which is a very widely used concept in peer-to-peer networking for peer discovery. It can also be backed by rendezvous nodes. It can be backed by things like MDNS for local peer discovery, and in the future we'll be able to use Bluetooth and FS and even hybrids of these systems, because one of the problems of discovery networks is always a recurring problem is bootstrapping, right? So how do I get the first seed of peers to actually be able to interact with the rest of the network? And there are some interesting approaches that can be done on that layer by using hybrid approaches. Cool, so I won't go very deep into this. Content routing is something that the libp2p stack also provides. It's also a pluggable interface, which is normally implemented by a DHT. So content routing gives you the ability, essentially, of locating content address pieces of data in the world. Another functionality of the libp2p stack is PubSub. So PubSub is a message-oriented communication pattern, which is in contrast to request-reply communication patterns. In PubSub, there are publishers of messages that are sending messages pertaining to a particular subject or a particular matter, and that matter is normally called a topic. So publishers are publishing messages on topics, and there are subscribers around the world that are wanting to receive those messages. And it's basically an M2N communication pattern. And it is inherently asynchronous and decoupled in nature. There are no timing conditions. When a publisher sends a message, it doesn't know who is listening for that message, who it's going to arrive to. It just knows that it's emitted a piece of information, right? So we have a number of properties. So peer-to-peer PubSub is a difficult problem. You can imagine in centralized systems and in enterprise systems, PubSub is a very widely used approach. So if you've used something like ActiveMQ, Kafka, or whatever, then you will have been familiar with what PubSub is. But in peer-to-peer networking, it is orders of magnitude more difficult to create a attack resistance PubSub network. And there are a number of characteristics. I won't go into it, but if you're really interested in this, then come find me. The libp2p stack provides 2 different routers for now. For PubSub, we've got FloodSub, which is a very naive router, and we've got GossipSub, which is the thing that Ethereum 2.0 is building on. And GossipSub provides a layer, a base layer in primitives to build adaptive PubSub networks, adaptive and self-optimizing and resilient networks. It is not a solution by itself. It is a building block. It is a primitive to build intelligent routing mechanisms like EpiSub. So EpiSub is one that I'm very excited about. It's a combination of 3 different approaches that are part of that exist in the state of the art, but it's a very particular combination that I think it's going to give very good characteristics as we go forward. Right. So another thing that the libp2p stack provides is relaying. So in many cases, you will have 2 peers around the world will not be able to immediately interact with one another because one of them is sitting behind a NAT, right? So circuit relaying is a feature that allows 2 peers to interact with one another via a 3rd peer in a secure fashion, right? And this is a picture from IPFS camp in Barcelona a few months ago, and that's Kumavis and people from the MetaMask team probably have seen them before, and they basically got this pipe around their neck and kind of like portraying what relaying looks like. It was a very cool exercise. Now, relaying by itself is costly, it's ineffective, and you don't want all your traffic to go through a 3rd-party provider, even if that 3rd party is not able to see the contents of those messages, right? It's very inefficient, and it creates centralized pockets of communication in the network. So really what we want to get to is something called decentralized hole punching. I'll talk about this in a second. But before that, just wanted to say that libp2p provides 2 features, AutoNAT and AutoRelay, that basically AutoNAT senses whether a peer, whether a node is running behind a NAT, and if it does, it activates the relay subsystem automatically. So the relay subsystem will look for peers in the network that are acting as relays. It will connect to those peers, bind with those peers, and then it will start publishing relayed addresses for the peer that is sitting behind a NAT. So that will essentially make that peer connectable from the outside world. Now, I talked about decentralized hole punching, the whole idea, and I have one minute and a half left. I think I'll make it. I did say that this was going to be high speed and high bandwidth and high throughput. So there you got it. So hole punching is very exciting. This is currently undergoing active implementation. Hole punching is the idea that there are certain mechanisms that peers can use to pierce through NATs, to burst through NATs, right? To create port openings in NATs. Relaying all of the traffic between 2 peers is very inefficient. So instead, what we want to do is when we establish that relay connection between 2 peers, we want to use that as an embryonic connection to start signaling for hole punching. So when you establish a relay connection, both peers will start a synchronization procedure to decide when is the right time to start sending messages, very appropriately crafted messages to try to break through their corresponding NATs to establish a direct connection. And if that thing succeeds, if establishing a direct connection succeeds, what libp2p does, what libp2p is going to do is transplant the connection state into that new underlying direct connection between those peers. Okay, so let's talk a little bit more about the future. I've already provided nuggets about what's coming down the pike, but I just wanted to make a list of stuff that I'm very excited about. So one of our main focuses right now is distributed reproducible testing. And we're shooting for the stars here, and we're aiming to test workloads on clusters of up to 100,000 nodes, right? This is super difficult. It is a very difficult problem that, from what I understand, hasn't really been attempted or hasn't been really had like long-term success in terms of being used actively and integrated in a continuous integration and development process. So this is something that we're focusing on. We're focusing on things like conformance test kits, better specs, network visualization, improving the DHT, as I said, not hole punching, episub, and many more things. Just wanted to provide you a bit of insight into the TESTGROUND effort, which is the testing platform that I discussed. This is just an architectural overview. We're not going to go into this. But if you're interested in this effort and what's happening, you can check out IPFS TestGround, the IPFS TestGround repo. This is probably going to move to the libp2p repo, to the libp2p organization soon. Yeah. And another thing that we're working on is also instrumentation. So we want to provide users with the ability to X-ray into what libp2p is doing under the hood, because the networking stack is very abstract, it's very difficult to understand what's going on under the hood, and giving visibility into that and observability is crucial at this point, especially as more and more projects are relying on libp2p for their mainnets. So the way that we're going about this is, first we're creating a standard introspection protocol that can be implemented by any libp2p implementation. We're taking a data-first oriented approach here, so that means instead of these are mock-ups of what we ideally want, this console or the web console to look like, but we're taking a data-first oriented approach, which means, hey, the first step is to make libp2p implementations actually emit fire hoses of data of everything that's happening under the hood, right? Once we got that, we are creating a set of libraries that can consume that fire hose of data on a browser and populate a local state, a reactive state, such that React-based D3 visualizations will be able to hook up to it and be driven by all of that fire hose of activity that's happening within a libp2p node. Of course, another thing that we'll be able to do is record libp2p activity, a fire hose of libp2p activity, and then reproduce it and play it over and over again in a browser as well. So I think that's pretty much everything that I had for today. Yeah. I just wanted to say that we're libp2p everybody here. And if you want to get involved in shaping the future, hacking on meaty things, or contributing, then you have all of these venues. And there's also a dev grants repo for stuff that we want to do, but we don't have the capacity to do in the libp2p team. And we're willing to incentivize the community to work on these things. These are my contact details. So if you want to hit me, find me around, or follow me on Twitter, or email me.
Thank you very much.